In this video, I'll be showing you how to solve logarithmic equations. So let's go ahead and get started here. We have log base 5 of x is equal to 3. Now I'd like you to think about how you might solve this, based on something we've already learned. Now, what I hope came to your mind is that this is in logarithmic form. We have a base of 5, the exponent is 3, and the answer is x when we're in this form. And we can change this to exponential form. So we're going to change forms. That's going to be our first technique or method for solving logarithmic equations. So there's just going to be two. So let's go ahead and switch forms here. We get 5 cubed is equal to x. Now I want to remind you that we talked about what I call the round the worlds, where we can check these when they're in log form. So it's 5 to the third power equals x. And so that's what we're doing here when we switch forms. Again, we have the three parts, and we're just rewriting this in exponential form. Of course, 5 cubed is 125, and so that's our answer. And I would remind you to always check your answers, especially with exponential and logarithmic equations. It's pretty easy to do. So here, let's go ahead and replace the x with 125. And again, we said 5 cubed is 125, and of course that's true. And so this one does check. All right, let's move on to the next problem. So natural log of x is equal to 3. Now, what you may want to do is, we know that ln stands for natural log, which means our base is e. We don't normally write the e, but we can certainly put one in there. And so now we'll do the same thing we just did. Again, it's base, exponent, answer. So e to the third power equals x. And so now you can get your calculator, and you'll find that that's 20.0855. Let's go ahead and check this. It's pretty easy to check. You'll just take the natural log of 20.0855, and when you plug that into the calculator, notice I'm rounding to 4 decimal places. I think it's going to be 3 or 4 when you do the problems in your homework. But in any case, the answer is rounded, so it'll be close to 3. It won't be exactly 3. Normally it won't be exact when you check, but it should be close enough that you'll know that it's right. All right, so that checks. Let's go ahead and look at a third one here. So I would encourage you to go ahead and do this one and then watch the video. Okay, so I would put in a base. My base is 10. Remember, this is what we call a common log. And so when we switch forms, it'll be 10 to the negative 2 power is equal to x. Whoops. And so let's go ahead and write it in exponential form. Now we know 10 to the negative 2 power, let's see, that's 1 over 10 squared, or 100th. And so that's our solution. Let's go ahead and check this. So the log of 100th equals negative 2. And you could actually plug that into your calculator and verify that it does equal negative 2, and that one will be exact. All right, so let's go ahead and move on. There's 2 more problems that we're going to do. Again, you might want to try them first and then watch the video. So here, when you switch forms, again, it'll be 5 to the second power is equal to, in this case, a binomial, x minus 7. And so 5 squared equals x minus 7. Of course, 5 squared is 25. And we'll add 7 to both sides, and we get 32. So when we go to check this, it'll be the log base 5 of 32 minus 7 is equal to 2. Well, that's the log base 5 of 25 is equal to 2. And to check it, we'll just think of it this way. 5 squared is equal to 25. Well, of course, that's true. All right, so that one checks. So there's one more very similar to this one I'd like you to try. It's the log base 2 of the quantity 4x plus 1 is equal to 5. All right, so again, just like in number 4, we'll switch forms. We get 2 to the 5th power equals 4x plus 1. And of course, 2 to the 5th power is 32. And let's see, we've got a couple steps to get x by itself. We'll subtract 1 on both sides. We get 31 is equal to 4x. And so now to reverse multiplication by 4, we'll divide each side by 4. We get x equals 31 over 4. And again, this is pretty easy to check. I'm going to go ahead and plug in 31 over 4 for x. So notice when you multiply here, these 4's cancel and you get 31 plus 1. So we'll get the log base 2 of 32 equals 5. And to check it, we know that 2 to the 5th power should equal 32. And you can verify that is true. And so that one does check. All right, let's move on. So I want you to look at number 6 here, and I want you to notice how it's different than what we've been doing. This side over here is not a single value, which is what we've had. It's not just a single number. We actually have another log here. So basically we have log equals log, and these are both base 3 logs. So I want to talk about, so we've already talked about one method for solving logarithmic equations, and that was the one where we switch forms, or we changed the forms, and we would change from log form to exponential form, and that enabled us to solve for x. Well, I want to remind you here, so we have two methods. We already talked about the changing forms method. So I want to remind you of a property that we looked at earlier when we were solving exponential equations. B to the m power equals b to the n power if and only if m equals n. So for example, if we had like 2 to the x plus 4 equals 2 to the, we'll say 4x, then we would set the exponents equal since our bases were equal. So basically, if 2 powers of 2 are equal, the only way that could possibly be true is if the exponents are equal. So let me go ahead and erase this. Similarly, it's true when you work with logs. If you have the log base m of m, the log base b of m equals the log base b of n, then m will equal n. In other words, these are both base b logs. So the only way that these two logs could possibly be equal is if these inner numbers are equal, or I call them the inner parts. So it works very similar to the property we were using for equal bases. So I call this the equal logs method. And basically all we're saying is if we have two logs that are equal and they're both the same base, then the inner parts must be equal. All right, so let's go ahead. Actually, we'll be using that shortly. We're going to use it right here, and then we'll use it in some of the problems we get to later. So if you look at the problem here on number 6, these are two logs that are equal, and they're both base 3 logs. And so the inner parts must be equal. 2x must equal 5x minus 4. So let's go ahead and we need to get x on one side only, so I'm going to subtract 5x on both sides. We get negative 3x is equal to negative 4, and I'll divide both sides by negative 3, and you get 4/3. Now to check it, let's go ahead and plug in 4/3 into the original equation. Now on the left side, you have 2 times 4/3. That's like 2 over 1 times 4/3. When you multiply, you get the log base 3 of 8/3. Now on the other side, when you multiply here, you're going to get 20/3 minus 4. And if you have to, use your calculator to help you do that, but you end up getting the same thing, the log base 3 of 8/3. And so these are equal. All right, so let's move on and continue working on solving logs, logarithmic equations. So if you look at number 7 here, this is a little bit different than what we've done before. At least as a first step, I'm looking at the fact that there's 2 logs on the left, and that's not like what we've been dealing with. So if you think back, there's some properties we have that can help us here. So I'm going to go ahead and remind you of a couple properties. So first of all, this is the product rule. The log of some product, in this case m times n, is equal to, well, it's a log base b of m times n, is equal to the log base b of m plus the log base b of n. So basically, we actually have what's on the right here. We have a sum of two logs here. And so we're going to be able to write that as the log of a product. So we'll be using this property. The other one that I would remind you of is the quotient rule, which is this one here. So in this case, we will be using property 1. We're going to combine the two logs on the left together, since it's a sum of logs like what we have here. We're going to write it as the log of a product. So the log of x times x minus 9 equals 1. Now keep in mind our base here is 10. This is a common log. Notice the base hasn't been written. So I'm going to go ahead and put a 10 in there. And now I'm just going to, now remember, we have two methods to solve this. We can switch forms, or if we have log equals log, we have a way to solve that. Well, this is not log equals log. This is the case where we're going to need to switch forms. We have the three parts. We have a base, an exponent, and an answer. So again, if you use round the world, it looks like this. We have 10 to the first power is equal to x times the quantity x minus 9. Now let's go ahead, don't really need that exponent 1. Let's distribute on the right. We get x squared minus 9x. Now this is a quadratic equation, so we want to get 0 on one side. Let's subtract 10 on both sides. So we get 0 is equal to x squared minus 9x minus 10. Okay, so this is quadratic. We're hoping we can factor this using the AC method. We need two numbers that multiply to negative 10 and add to negative 9. And you can try figuring it out. You should end up with 1 times negative 10 and 1 plus negative 10. Let's go ahead and plug those numbers in. And so when we solve for x, we get negative 1 and 10. Now at this point, I need to remind you of something, or actually bring something to your attention. It's something we looked at before, but not really in the context of solving equations. So what if, so we're going to plug in the negative 1 and the 10 into the original equation to see if they are solutions or not. We're going to check our answers. But I want to remind you of something about the log, or the graph of a log. We have y equals the log of x. We're dealing with base 10 logs here, so I'm going to go ahead and graph this. We know because of the fact that it's a logarithm, it goes to the point 1, 0. Looks kind of like the ET function, but it goes kind of like that. And so I want to just look at this a little more closely. What's the domain of this function? Well, that would be 0 to infinity. We don't quite get to 0 here, and then notice it goes forever to the right. So what does that really mean when we say the domain is 0 to infinity, not counting 0? Well, really that means our x is greater than 0. So this value that we're taking the log of can't be anything that's negative. It can't be 0. It's got to be a number that's positive. All right, so notice if you're checking negative 1 here, when I plug a negative 1 in for x, log of negative 1, I can't do that. It's undefined. I mean, you could try putting it in your calculator. It's not in the domain. We cannot take the log of anything unless it's a positive number. Can't be 0, can't be negative. And so negative 1 does not check here. I'm going to go ahead and check 10. The main thing you got to watch out for with these is that you don't end up taking the log of a negative when you plug the x value back into the equation. And it could happen in either case. In this case, if you if you replace both of these x's, you end up taking the log of a negative in both cases. But it only has to happen once, and it causes your solution not to work. So we're trying 10 here. We have the log of 10. Remember, our exponent here is 10. So this is the exponent you put on a base of 10 to get 10. Of course, that would be 1. Whoops, I didn't go to that next line. It's log 10 plus log of 1 equals 1. So we just said log of 10 is 1. You can also check that on the calculator, but I think it's important to also be able to evaluate without the calculator. Again, for log of 1, this is a base 10 log. Whoops. Let's make that a 10. So what exponent do you put on a base of 10 to get 1? That would be 0. And so log of 1, whoops, is 0. And so 1 plus 0 is 1. This one does check. All right, let's move on to number 8. And I would encourage you to do this one. It's very similar to the one we just did. And then watch the video. All right, so we're going to use property 1 again. We have a sum of 2 logs. And so we're going to write that as the log of our product. So basically we're just going to multiply these two together. And so we're going to get the log base 3 of x plus 6 times x plus 4, and that's equal to 1. So now this is just like the last one we did. We have the 3 parts. We have a base of 3, an exponent of 1, and the answer is this product here. Or again, you can use the round the worlds. 3 to the first power is equal to what's here. And so we end up changing forms here. This is the type of problem where we switch forms. So we get 3 to the first power is equal to the quantity x plus 6 times the quantity x plus 4. Let's go ahead and simplify this. When we FOIL it out, we get x squared plus 4x plus 6x plus 24. Let's combine our x terms there. We get 10x in the middle. We'll subtract 3 on both sides. We get x squared plus 10x plus 21. So this is a trinomial. We're going to try to factor this. I need 2 numbers that multiply to 21 that add up to 10. Of course, that would be 3 and 7. And so when we solve for x, we get negative 3 and negative 7. All right, now I can see that if I plug in negative 7 up here, and it'll be in both cases, but negative 7 plus 6 here is negative 1. I'd be taking the log of a negative. Of course, we can't do that, so I know that negative 3 is not going to work. You can go ahead and plug in negative 7. Oh wait, I said that wrong. Negative 7 doesn't work, but negative 3 does. Let me go back and fix this here. I crossed off the wrong one. So it's the negative 7 that's not going to work, and I'll go ahead and show you that negative 3 does work. When you plug in negative 3, you end up with the log base 3 of 3 plus the log base 3 of 1 equals 1. Well, the log base 3 of 3, we're saying, okay, that's the exponent you put on a base of 3 to get 3, and of course that would be 1. And here, whoops, I forgot to write my 3 here. What exponent do you put on a base 3 to get 1? Well, that would be 0. And so 1 plus 0 does give you 1. So notice this one does check. So only the negative 3 checks on number 8. All right, let's move on to the next problem here. So on this one here, notice this is a difference of 2 logs. So I would encourage you to try this one. It's just once you get to the equation that you'll be solving, it's a different kind of equation. But the process is the same, other than you're going to be using the quotient rule. All right, so oops, let's see. We have the log base 4 of x plus 2 over x minus 1 equals 1. So we're basically using the second of those two log properties that I looked at earlier. And then now we're going to switch forms. So it'll be 4 to the first power is equal to x plus 2 over x minus 1. Of course, 4 to the first power is 4. I'm going to go ahead and multiply both sides by x minus 1 to clear the fractions. You get 4x minus 4. On the other side, the x minus 1's cancel, and you get x plus 2. We need x on one side only, so let's subtract x on both sides. We get 3x minus 4 is 2. So add 4 to both sides, we get 3x equals 6. So finally divide by 3 and you get 2. All right, let's move on to number 10. All right, so here notice we're going to combine these two logs together. We can use the product rule, but notice it's going to be this other, we're going to need to use our other technique for solving logarithmic equations because we're going to have equal logs here. The logs, we're going to have log equals log. So let's go ahead and use the product rule to simplify the left side. We'll get the log base, or the log of x times x plus 4, base 10, equals the log of 12. So again, these are both base 10 logs and they're equal, so the inner parts here must be equal. And so that means that x squared plus 4x will equal 12. Let's go ahead, notice I distributed on the left. Let's go ahead and, since this is quadratic, we want to get 0 on one side. So I subtracted 12 on both sides. And when you factor this, we need two numbers that multiply to negative 12 that add up to 4. Well, let's see, that would be 6 and negative 2. Notice 6 times negative 2 is negative 12, and 6 plus negative 2 is going to give you the 4. So our solutions will be negative 6 and 2. But again, notice we have a problem here. If we plug in negative 6 right there, we'd be taking the log of a negative, so we know that can't happen, so we'll cross that answer out. And I'll leave it to you to check that the 2 does work. All right, let's go ahead and move on to the last one, number 11. All right, and I would encourage you to try this one and then check your answer on the video. All right, so notice on the left side we have a difference of logs. So we would use the second property just like we did in number 9, and this would be the log of x plus 14 over x plus 6 is equal to the log base 3 of x. And again, these are both base 3 logs, and these two logs are equal, so this is the equal logs case. And so these inner parts must be equal. So we're going to have x plus 14 over x plus 6 is equal to x. I need to clear the fractions, so I'll multiply each side by x plus 6. On the left, we end up with x plus 14. On the right, we're going to get, when we distribute, x squared plus 6x. I'm going to go ahead and move this up here so we have a little more room to work with. Now again, this is a quadratic equation, so we're going to want to get 0 on one side, everything else on the other. So I'm going to subtract x on both sides and also subtract 14. We end up with 0 equals x squared plus 5x minus 14. Now when you factor this, you need two numbers that multiply to negative 14 and add to 5. And you can verify that 7 and negative 2 work. So our solutions will be negative 7 and 2. And I want you to notice if I plug negative 7 in here and here, that I have a problem right here because I'd be taking the log base 3 of negative 1. So we know we can't take the log of a negative, so the negative 7 is out. And you can verify that the 2 does work. All right, and that's the end of this video.